All right, let's jump right in. Today, we're going to tackle one of the most famous, most important limits in all of calculus. You see it absolutely everywhere. But the proof, the proof is this beautiful, elegant argument that's all about geometry. So let's get into it. So here's the puzzle we're trying to solve today. What is the limit of sine of x over x as x gets really, really close to 0? Now, on the surface, it looks pretty straightforward, right? But there's a tricky little trap hiding in there. So why is this such a big deal? I mean, why can't we just plug in 0? Well, let's try it. If you plug in x equals 0, you get sine of 0 on top, which is 0, and you get 0 on the bottom. So 0 over 0. And in math, that's what we call an indeterminate form. It basically tells us absolutely nothing. We're stuck. We need a much cleverer way to figure this out. Okay, now I know what some of you are thinking, especially if you've been through calculus. You're screaming, just use L'Hopital's rule. And that's a great thought, but here's the thing. That's the trap. To use L'Hopital's rule, you need to take the derivative of sine of x. And guess what? The proof for the derivative of sine itself depends on us already knowing this exact limit. It's this perfect, inescapable loop. You can't use the answer to find the answer. So yeah, we've got to find another way in. So, what's our clever workaround? Well, it's one of my favorite tools in all of calculus, honestly. It's called the squeeze theorem. Some people call it the sandwich theorem, which is pretty descriptive. It is the perfect, elegant tool for this exact puzzle. Okay, so what is this squeeze theorem? Here's the basic idea. Imagine you have this function, let's call it f of x, and its limit is just a real pain to figure out directly. But what if you could find two other, simpler functions, one that's always above it and one that's always below it? You've squeezed or sandwiched your mystery function. Now, if those two outer functions both head to the exact same point, well, where else can the middle one go? It has no choice. It gets squeezed right to that same limit. Yeah, this quote really nails it. We're changing the game. We're not going to attack this limit head-on anymore. Our new mission is to find two nice, friendly functions that can act as an upper and lower bound, and trap our function, sine of x over x, right between them. And this visual just makes it so clear, doesn't it? Look at that blue function in the middle. It's bouncing all over the place, kind of chaotic, but it's totally trapped. It can't go above that green line, and it can't go below that red line. So as the red and green functions come together and meet at that one point in the center, the blue function is forced to go there too. That's the squeeze, right there. Okay, so this is all great in theory, but where are we going to find these magical bounding functions for sine of x over x? Well, the answer, believe it or not, comes from geometry. We're going to use a unit circle to literally draw a picture of our proof. This is where it gets really cool. All right, let's look at this diagram. We're focusing on the unit circle, and we've got this small positive angle, we'll call it x. Now, within this little slice of the circle, we can actually see three different shapes. First, there's the small blue triangle inside. Its area, it turns out, is 1/2 sine of x. Then there's the whole pie slice, or the circular sector. Its area is 1/2 x. And finally, there's that bigger red triangle on the outside that contains everything. Its area is 1/2 tangent of x.
Okay, now for the part that's so simple, it's brilliant. Just look at it. You don't need any fancy math to see that the area of that small triangle is smaller than the area of the circular sector, right? And the area of the sector is smaller than the area of that big triangle. It's just visually true. This simple, obvious fact is the key to the entire proof.
So now let's just take those area formulas we just figured out and plug them into that inequality. And boom, we get this. 1/2 sine of x is less than or equal to 1/2 x, which is less than or equal to 1/2 tangent of x. We've just translated our picture into pure algebra. This is the heart of the argument. All right, we've got our geometric inequality. The hard part's over, in a way. Now it's just a matter of algebraic manipulation. Our one and only goal right now is to rearrange this thing until we get sine of x over x stuck right there in the middle. First step is easy. See all those 1/2s? Let's just multiply everything by 2 to get rid of them. That cleans it up real nice and leaves us with this fundamental relationship. Sine of x is less than or equal to x, which is less than or equal to tangent of x. Okay, for our next move, let's divide the entire thing by sine of x. So on the left, sine of x divided by itself is just 1. In the middle, we get x over sine of x. And on the right, well, remember, tangent of x is just sine over cosine. So if you divide by sine, you're left with 1 over cosine of x. Now hold on, we're so close, but the thing in the middle is x over sine x. It's the reciprocal of what we want. No problem. For our final move, We just take the reciprocal of everything. Now, you have to remember a key rule of inequalities. When you flip everything, you also have to flip the signs. And just look at what we're left with. After flipping, we have cosine of x is less than or equal to sine of x over x, which is less than or equal to 1. We did it. Our function is perfectly isolated. We have our bounds.
Okay, take a breath. We have done all the heavy lifting. We built the geometric picture, we did the algebra. Now comes the easy part, the payoff. It's time to finally use the squeeze theorem. So let's check our two sandwich functions. What happens to them as x goes to 0? Well, the lower bound, cosine of x, what's the limit of that as x approaches 0? It's just cosine of 0, which is 1. Easy. And the upper bound? Well, that's just the number 1. The limit of a constant is just itself, so that's also 1. Both of our guards are heading to the exact same spot. So think about it. If the function below is heading to 1 and the function above is heading to 1, then by the squeeze theorem, our function, sine of x over x, which is trapped between them, has absolutely nowhere else to go. Its limit must also be 1. And that's it. A really beautiful, rock-solid proof for one of the most important limits in calculus. But why do we care? Why do we go through all this trouble? Well, this isn't just some abstract puzzle. This limit is the absolute cornerstone for finding the derivatives of sine, cosine, tangent, all of them. But even more than that, it gives us something incredibly useful called the small angle approximation. It basically says that for really tiny angles, sine of x and of x itself are almost the same number. And this little shortcut is a lifesaver in physics and engineering, letting people simplify incredibly complex problems. You know, what I love about this proof is how it weaves together geometry, algebra, and the idea of limits into one beautiful story. It's a great reminder that sometimes the most powerful tools in math aren't complicated formulas, but elegant ideas. It really makes you wonder, right? What other beautiful proofs like this are just hiding out there in plain sight?